Okay, so, right, I will review a couple problems we posted last Thursday. It's about the conditional independence. Okay, so we have considered f sub j is the just coin is selected, and so they are k plus 1 coins. Okay, so index is from 0 to k, and we know that because we select coins randomly, so the probability of this event will be equally probable, so will be 1 over k plus 1. Okay. And the given event is that G is the first n flips. So once we stack a coin, now the first n flips all result in head. Okay, so that is the given event G, and the event we want to know is that the n plus 1 flip, okay, results in a head again. Right. So what we want to compute that the conditional probability of event E given event G. Okay, so that this is our purpose. Okay, now. So last Thursday, results. Okay, we compute that given the just coin is selected. We want to know that, okay, and then in that time, I write here that this probability becomes to be, okay. The second statement is that I wrote and ask you to check whether this is true or not. Okay, and so first of all, for the first statement, this the equality is true. Only for J from 1 to K. Right, but it's not equal to since okay, if J equal to 0, since the probability that f is 0 intersect G is 0. So, okay, so we cannot apply proposition 3. I think it's 3.4. 3.5.b. Because because this identity is by applying proposition 3.5.b. But the required condition for applying proposition 3.5.b is that this probability must be non-zero. Okay, but when j equals to 0, okay, this joint event has 0 probability. Why? Why? Because when the zeroth coin is selected, then the probability to have a head is 0. Remember, right? This probability is 0. Okay, so G is that the first n flips all results in head. Okay, so you select the zeroth coin, and then the first n flips give you heads. The probability is 0, of course, because once the zeroth coin is selected, when you flip that specific coin, the probability to have a head is 0. Okay, so this is 0. So that's why when j equals to 0, this is not true. Okay, this is not true. Okay. All right, so this is true only for j from 1 to k. Now, for this identity, this is incorrect. No, it is incorrect. Okay. All right, so I will examine. First of all, the computation of the first statement is here, right? Now, since events E and G are conditionally independent, given the just coin is selected. So once we select a coin, then we have perform independent tossing of coins, right? Because when a specific coin is selected, we use that coin to do tossing. Okay, and the tossing, every trial is independent of each other. So given this event, event E and event J will be independent. Why? Because event G involving the first n flips, okay, but event E involving the n plus 1 flips. Okay, and we know different flips are independent given a coin is selected. Okay, so that with this probability condition, this conditional probability function, okay, right? So under this probability measure, we know this is independent. So we know that we have this one by proposition, by applying by applying proposition 3.5.d. Because in proposition 3.5.d, that if we have conditional independence, then we have this one. Okay. All right, and given the just coin is selected, then the n plus 1 flip have a head with probability which is equal to j divided by k. Okay, so we immediately have this two-level condition probability here. Okay. Any questions about the computation of this one? All right. So this is good for every j. Okay, for every j. All right. So the argument is by applying proposition 3.5.d. Okay, directly. Now our purpose is to compute this one. So this is not true, okay? Now, okay. Okay, so this is actually so with this conditional probability functions, and then we apply the decomposition formula. Okay, right. So j is from 0 to k, and the PG fj j here. All right, so by applying the decomposition in section 3x3, all right, to PG, where F0 F1 up to F sub k is a partition of the sample space. Okay. Okay. Now, if we want to use proposition 3.5.d to this is the two-label conditional probability, right? But be careful. If you want to turn the two-label conditional probability to one-label conditional probability, you have to make sure that the probability of the joint event G and the Fj should be positive. But once again, if j equals to 0, then this joint probability has 0 probability. Okay, so you will get into trouble. Okay, so that if j is from 1 to k, then no problem. You can apply proposition 3.1.b. But if j is 0, then you can't. Okay. Well, so we first examine this probability because this is the one-label conditional probability. This is easier to attack, right? Now P, G, F, J. Okay, so this is the right. So by by the definition of conditional probability, we have this. All right, so basically we apply the Bayes formula. So this is actually I from 0 to k, and the PFI, PG given FI. And this one is P of Fj, P of G given Fj. Okay, so this is by Bayes formula. Again, things F0, F1 up to F sub k is a partition of the sum of space. Okay. All right. Now, this conditional probability is easy. Right. So this is Pfj of G. Now, if the chess coin is selected, okay, the coin is selected, then the tossing coins becomes to be independent, right? Right. So, and G, what is G? G is that the first n flips with all result heads. Okay, and so J over K is the probability that the chess coin, when we flip the chess coin, a head appears. Okay, so that this is the probability, and because that they are independent trials, so if you get head n times, then the probability will be the nth power of this ratio. Okay, so that is easy thing to have. All right, and remember that the coins is selected randomly. Right. So what we have? So now we have 1 over k plus 1, and this one is j divided by k to the nth power, and the denominator I is 0 from k, and 1 over k plus 1, and here is I divided by k's nth power. We have that. Okay, right, and so we just cancel the common factor here. So we have j, okay, nth power, summation I. But when I equal to 0, when I equal to 0, this is 0. So the index we can start with 1 to k, and I divided by k, nth power. Okay. And specifically, and we know that F0, so this conditional probability oh, it's the condition, we know P, G, that it's actually the conditional probability function. We prove that conditional probability can be regarded as a function, right? If G is given. So it's a conditional probability function. Yes. Yep. Right. So this is actually, whenever I write conditional probability function, because I want to apply general probability for any probability function. Because there's a lot of general probabilities for probability function in chapter 2, right? We derive a lot of properties. For example, property in section 2.4, right? for example, the inclusion-exclusion identities, right? We have a lot of them. Okay. So, and also we derive a decomposition formula for probability function. We have multiplication rule, right? So there are some of the results we can apply. And these results all good for any probability function. And then we prove that conditional probability function is a kind of probability function. Okay. So that is. Now, so if J is 0, all right, we know this is 0 here. Okay? When J is 0, so we know this is 0. Okay, and so the summation, because this is when J equals to 0, this is 0, so the summation can be reduced. So now probability of E given G becomes to be J from 1 to K. Okay, so J from 1 to K. So we avoid the case that J equal to 0. Okay, because that when J equal to 0, this is 0. So we, okay, right? So we have PG given FJ and P. G E given Fj. Now this two-level probability, okay, equal to P Fj E given G. Okay, by proposition 3.5.b, since probability of Fj intersect G equal to okay, this is okay, this is greater than 0 for all J from 1 to K. Okay, so the joint probability, when we compute them, is positive. Okay, for all J from 1 to K, they are positive. So we can apply proposition 3.5.b. All right, so we can exchange. Okay, change the role of Fj and G. Okay, and but this is equal to Pfje, right? Here by conditional independence. Okay, and we know this is equal to J divided by K here, as we have computed here, right? As we have computed here. Okay, so now, okay, here, and we have computed that this is equal to summation I from 1 to K, I divided by K to the nth power, and J divided by K to the nth power, times J. Okay, now, because the denominator is, right, so that each term has the common denominator, so this is K. Okay. And the summation here, J divided by K, raised to n plus 1's power, because we multiply this into that. So this probability becomes to this ratio here. Okay. Now what is the ratio? Okay. Now we see that when K is big, is large. Okay, we know the summation nth power is approximately the integral, okay, for x to the nth power dx. Okay. Okay, and here the delta x is 1 over k. So if k is big, then 1 over k is quite small. Okay, so this summation can be approximated by this integral. Right, and this is 1 over n plus 1. Okay. Right, and secondly, j from 1 to k, I'm sorry, to k. To k and j, okay, n plus 1, approximately n plus 1 dx. So this is about again okay, so now, so if we multiply here 1 over k in the numerator and the denominator, okay, so this is approximately equal to n plus 1 divided by n plus 2. So this is a good example to illustrate that you have to be careful when you want to apply proposition 3.5 to B to turn two-label conditioning into one-label conditioning. Okay, you have to make sure that the joint probability has to be positive. Okay. Okay. Any questions? Okay. Yes, please.
Why with k over k is bigger than 1 is equal to 2?
Oh, okay. So, okay. Okay, for k equal to 5, 6, okay. Right. And suppose n equal to 2. All right, so we have about here. This is the parabola. Okay, and so we have here. Okay, the height here. This is so here we have 1 over k, 2 over k. So maybe I use 6. Now the width always 1 over 6, so x is. But the height here, this is square, and the height here, the height, I think here, square. The height here is square. Okay. So this is the width. This is the width, and this is the height. Okay. So the summation is the area here, is the yellow part. Okay. So of course, for this case, the yellow part is always bigger than the integral from 0 to 1, right? But as k goes to infinity, then you can prove that the yellow area is equal to the area under the curve. Okay, under the curve, f of x equal to x to the nth power. Okay. So when you learn the integral calculus in your freshman year, so you should know that we can approximate integral by areas. Okay. Okay. So when k is really big, then we have the sum here will approach to this integral here. Okay. So can be well approximated by the integral. Yes, please.
This is the Riemann sum. Riemann sum. That's what it's called, right? Yeah.
Riemann sum, yes. This is Riemann sum, yes. But for Riemann sum, you can select the height can be selected to be any function value in between this interval. Riemann sum says that you can select any. Here, I will just select the endpoint here, right? You can select endpoint here. But Riemann sum give you the degree of freedom to stick arbitrary value. Okay, and here the second interval you can stick arbitrary value. Yeah. In this construction, we just select the value corresponding to the right end of each interval. Okay. Yeah. So this is one of the Riemann sum. I just say one. Okay, there are many possible infinite sums. But we say a function is Riemann integrable, means that whenever you select for the height, they should be converged. They should converge to the same value. Okay, as k goes to infinity. Okay. And in calculus, we have proved that if a condition is continuous function, then it's in a finite interval, then this function is Riemann integrable. Okay. So any standard textbook give proof for that fact. Okay. Any other questions? Okay. All right. So, so always remember that this example gives us the lesson when we want to apply proposition 3.5.b. The required condition has to check. All right, you have to check the required condition before you can apply proposition 3.5.b. Similarly, when you want to apply proposition 3.5.c, then there is a condition, all right, a sufficient condition you have to check. Okay. Otherwise, you will be in danger to solve the problem. Okay. All right. So if no other question, then we will discuss chapter 4 about random variables. Okay, and actually this chapter deals with discrete random variables, okay, a special type of random variables. But because of the title of this chapter, so I would like to give an exact definition of a random variable, no matter it is discrete or not. Okay, all right. So this concept, this section, I think is important. Okay. Yes.
So how much of what we have learned so far are we going to use for this chapter? I mean, if we have some doubts in previous concepts, is it going to affect this?
Yeah, you will see they are related to each other. Because in chapter 3, in chapter 2, we learn how to assign probability to arbitrary events of interest. We collect all events of interest into a collection, has some structure, where we can do countable many complements, intersection unions. So that structure we call sigma algebra. So every members in the sigma algebra we call an event of interest. Because for each event of interest, we want to assign the probability to it. All right, so we learn how to assign probability with a reasonable structure, right? So for example, the probability function should satisfy countable activity. Right, so that is the one. And so that it deals with all events of interest. But in applications, that event of interest should be described by some means, right? Random variable is a very common means to describe events of interest. I will explain that.
So mostly from chapter 2?
Yeah, so chapter 2 is very important. Chapter 3 is also because it's about conditioning.
Because, yeah, I have some doubts in chapter 3, so I'm afraid if you're going to use those concepts.
Because we will see, we will learn that, okay, so that we will learn, given a random variable has certain value, what is the probability that another random variable has another value? Okay. Given a student of NTHU has weight over 80 kilogram, all right, in this case. So what is the probability that this student has diabetes? Okay. That has a certain disease or some characteristics. Okay. So that the age or the weight or something, this is a characteristics of as an outcome of a random experiment. Okay. So I will address that immediately. All right. So when a random experiment is performed, we are mainly interested in some characteristic of the outcome. Instead of the outcome itself. Right? Just like you want to study a patient in a hospital. All right, so you randomly select a patient from the hospital. But a patient in a hospital, okay, this patient may have a different kind of diseases, okay, and they have different kind of the health conditions. So a certain study may focus on some aspect. For example, maybe study a specific cancer like lung cancer or maybe a heart attack or a lot of different kind of diseases there. Because a patient in terms of health condition will be very complicated. Okay? So we are mainly, so even though we just randomly select a patient, okay, we mainly interested in some characteristics of the outcome. Okay, so instead of the outcome itself. And in many situations, these characteristics can be expressed as real numbers. Okay, so here we have to do a random experiment. And after we perform random experiments, there is an outcome there. Okay, and then we may have different measurement devices. So number one, for example, you measure the blood pressure of this patient, for example, all right? Or you measure the temperature, body temperature of a patient. Number two, etc. And maybe you will measure some chemical compound, basically organic compounds, okay, in the blood of the patient. Okay, and this compound may be some indicators of certain cancers. Okay, so you may have a measurement. There's a lot of measurement. So number n. Okay, so the same outcome with different measurement devices, they gives you a different measurement result. All right, so this may be the x1, x2, and xn. And in a study, they want to, for example, they want to know the correlations of this n observed valued. Okay? Right. So with some indicator of cancers, and they want to know there are some factors which for doctors can predict that the probability of a patient to have a certain cancer. Okay. In modern medicines, that there are a lot of measurement devices like you can take the X-ray photography, or with the X-ray as a basis, you can do the so-called the CT, computer tomography, right? Computer tomography consists of a lot of X-ray figures. So they use the X-ray figures to construct a three-dimensional structure of part of your body. Okay, or you can use the NMR to do the scan of your brain or your bodies. It also consists of a lot of slices of your sections of your bodies, and to reconstruct something. Okay, so all these are measurement devices. So you have a lot of data there. Okay, and this data actually has noises. They have noises. So that then you want to use those data to predict that the probability of a patient to have a certain, for example, the brain cancer, something like that, and also the type of the brain cancers. The problem becomes to be more and more difficult if you ask some specific cancers, so that you are able to know what kind of drugs will be able to treat this kind of cancer. Okay, so it becomes to be more and more difficult. But all these things, they are based on a patient, and you do a lot of measurements. So you have a lot of we will see they are all random variables, and you should treat a bunch of random variables. Okay, to do statistical analysis. But the basic mathematical structure is probability theory. So you should apply probability theory as the foundation, all right, to statistics for you to do the so-called the inference, so-called the statistical inference. Okay, because no doctor say that you with 100% that you get a certain disease. Nobody can say that. They will say, okay, that there are very high probabilities. If they can say that over 90%, over two-thirds, something like that. Okay. Right. So, all right. So this is the real situations we have. Okay, and in the later, including this chapter, there are I think chapter 4, 5, and 6. Okay, especially chapter 4 and 5, we will see how random variables are used to describe events. Okay, so let me take a couple of examples. Of course, these examples toy examples are simple. Right? Real application would be very complicated. But everything, but the main idea can be seen from simple examples. So suppose that we toss a pair of dice, and we may be mainly interesting the sum of the two dice. Okay, so we are only interested in the sum of the dice, because in the certain gambling, right? The gambling, the game depends on the sum of the two dice. For example, to compare the order, right? The big and or small, right? Two party, and they just toss two dice, and with bigger sum will win. Okay, the bet, right? This is a very simple game. Yeah, maybe some of you played at childhood, but I played that too before. Okay, and so the probabilistic model SFP for this random experiment is here, the S, right? Because we know we are mainly interested in the sum, so the representation of a pair of dice will be described by a pair of integers, and note these two integers is in between 1 and 6, corresponding to the 6 faces of a die, right? So the outcome is here. And because the sum space is a finite set, so the sigma algebra usually is taken to be the power set of the sum space. And the P is the counting probability function, because that each outcome will have equal probability. Okay, so we usually take the counting probability function. Okay. Oh, sorry, model. Yeah. Okay. And with the counting probability function, we assume that these two dice are fair. They are fair dice. Okay. There are no tricky dice used. Okay. All right, and then we let x, right, to be a function from the sum space to the set of a real number by assigning an outcome ij to a value x of ij equal to I plus j. Okay, so once an outcome is observed, so once a pair ij is observed, then we form a value, which is just I plus j. Okay. Okay, so you can see the advantages of using a pair of integers to represent an outcome of the random experiments. Okay, because you have many ways to describe the outcomes of this random experiment, right? But this representation has advantage because it is easier to define the functions here. Okay. just like here. So the measurement device, so you can think about the measurement device is to, once the outcome is observed, and then from the outcome, it would give you a value here. So this is a value, a numerical value. All right, then x is a random variable. Since it satisfies the required general property as will be seen shortly. Okay, so we will show what is the required general property. Okay. But basically, a random variable is a real value function, has real value on the sum space. So the domain is the sum space, and the codomain is the set of all real numbers. Okay. Okay, before we take a break, then I would like to take a second example. All right, so in flipping a coin n times. So our running experiment is to flip a specific coin, all right, n times. All right, so in flipping, in this kind of running experiment, we may be mainly interested in the number of heads that occur all right, now the probabilistic model XFP for this running experiment maybe I say a fair coin, okay? A fair coin, which means that a coin will result a head or a tail with equal probability, okay? Okay, for this random experiment, X here is the sample space consists of a finite sequence, all right? And the sequence is binary. Right? So we have an n-tuple, a binary n-tuple here. N-tuple, we call this is n-tuple. And the components are binary, either 0 or 1. Okay? So 0 corresponding to tail, 1 corresponding to head. Okay? So we use 0 to indicate tail and 1 to indicate head, okay? So this is one of the representation, okay, for the sample space. And also, because sum of space is finite, so the sigma algebra we select is the power set of the sum of space, and the probability P is the counting measure. Because we use a fair coin, so it's the counting probability function. Okay. Now we let x to be a function from the sum of space to the set of all real numbers by assigning an outcome omega 1, omega 2 up to omega n to a value x of equal to summation I from 1 to n omega I. And omega I is either 0 or 1. So 1 corresponds to the head. So the sum gives us the number of heads in this outcome. Okay, so this representation gives us a numerical value. Okay, so that so you define a random variable. Okay, maybe. Okay. Then x is a random variable since it satisfies the required general property as will be seen. Okay, so the first thing you learned here is that any random variable is just a function, a real value function on the sum of space. Together, satisfying a specific general property we will describe later. Okay? Okay, so let's take a break up to 2:30. All right, so before we describe a formal definition of a random variable, we have to prepare a couple of concepts. Right, in chapter 2, the Borel sigma algebra B sub 0 to infinity on the infinite interval is defined to be the smallest sigma algebra which contains all subintervals of the infinite interval, 0 to infinity. Okay. Now, in general, the Borel sigma algebra could be of sub I on an interval I of the real line is defined to be the smallest sigma algebra which contains all subintervals of the interval I. So I can be any interval of the real line, okay? And you can see from 0 to infinity here, this is a specific interval only, okay? A member in scope B sub I is called a Borel set in I. Okay. In particular, when the interval is the whole real line, the Borel algebra, the Borel sigma algebra on R will be denoted as just scope B. So the scope B is actually the Borel sigma algebra on the whole real line. Okay, so it's here. So the concept. It's just a generalization from rows we have, because in chapter 2 we consider the lifetime of a light bulb, okay, and in that examples we encountered the Borel sigma algebra on the infinite interval, okay. All right, so this is about Borel sigma algebra on an interval. Now, we next introduce a concept of inverse of a function we done inverse function we done the inverse of a function when the function is 1-to-1 and onto, okay, in high school. Now, but to deal with a general function which may not be 1-to-1 or may not be onto, can we define a concept of inverse of that function? Right, so now consider a function f, okay, from a set A to a set B. In the terminology of set theory, A will be called the domain, right, of F. And the B is called the codomain of F. Okay? Now, for any subset E of the domain A, we define f of E so we collect all the values of elements in E together to form a set. Okay? So f of E, which is called the image of E under F, and is a subset of the codomain B. Okay? So for every subset of A, all right, there is a corresponding subset of B. Right? And then this established so this established a mapping over maybe a function. A mapping is just another name of function. From the power set of A to the power set of B. Also denoted as F here. So now F can be interpreted as a function from the power set of A to the power set of B. Okay, and with the assignment, is that okay? And it can be seen that is equivalent to contains exactly the same information of mapping as F to the S part, to the V part. Yes? E is a subset because 2 to the A is power set of A. The power set of A consists of all subsets of A. Yeah. So E is a member of this power set. And this is also a member of this power set. So this is element. E is an element of this set. And the image of E is an element of the power set. Yeah. Ah, maps to. Just like a function, we usually use the map to. This is the diction is from the domain to the codomain, but we use that to show the specific assignment. For example, if the assignment is here, then it's the quadratic function. Okay? Or if you have, so for example, okay, you give the logarithm, natural logarithm, right? So this is an expression of a function by elements. Okay. Good question, because I do not know you don't know this kind of notation. Very good. Yes. So indeed, when I were a student, especially when I were a graduate student, I usually raise my hand to ask my instructors every concept. Because there are a lot of things. For example, I am basically I am in the EE department in college. But in graduate school, I attended several courses in math department. For example, I took real analysis, complex analysis, functional analysis, a lot of things, or algebra, modern algebra. But because I'm not an undergraduate student in the math department, so a lot of basic concepts I didn't know. Okay. So I always ask my professor, "Oh, what is that?" Okay, and that is very convenient because then, professors were always very kind to answer my simple questions. Okay. Okay, good. All right, so we know we got ordinary function, okay, as functions, all right, on the power set of A, as functions on subset of the domain, okay. Now, with this interpretation, now we will, so now, on the other hand, right, for any subset G of the codomain, we define the image, the inverse image of G to be all the elements in the domain such that the value is in G, which is called the inverse image of G under the function f, and is a subset of A. Okay, so it's the image there. So we go back, right? G is so that this is A, the domain. This is B, the codomain. F here. Now, specifically, there is a G here, right? And then we go back to see what is the point, so that the A will go to here, inside here. So we look back and see all the possible elements in the domain such that their values is in G. All right, then this establish a mapping on a function from the power set of the codomain to the power set of the domain, denoted as F inverse. Okay, so F inverse to the B to the A by G goes to inverse image of G. Okay, so now we establish a concept of inverse of a function. Okay, so the inverse of F here is a set function. Okay, it sends a subset of the codomain to a subset of the domain. And the inverse function or inverse mapping has a nice property, and then I will describe in next proposition. Be a function from a set A to a set B. We let G sub I for I in index set I be subsets of the codomain B. Now, first property, the complement of G, and then with the inverse mapping, so we send back to A is equal to the inverse mapping of G, the complement of the inverse mapping of G. So inverse mapping and the complement commute. Second, if we take the union of all G sub I first, and then take the inverse mapping, it's the same as you take the inverse mapping first, and then take the union. So the union and the inverse mapping commute. Third, if you take the intersection, okay, of G sub I, and then take the inverse mapping, is equal to, you take the inverse mapping first, and then take the intersection secondly. So that, which means that intersection and the inverse mapping commute. Very nice properties. before we give a proof that, we make a remark. In comparison, we have only 2 prime. Okay. Now, for the forward mapping F, it is commute with the union. That's fine. It's correct. But F does not commute either complement or intersection. Okay. For example, suppose we have a function like this one. Okay, and the complement here, which is F3, and this K. All right, but this is not equal to Q, which is equal to complement. Now, F okay, so this is F of empty set. So this is the empty set, right? And this is not equal to K, which is the okay. Okay, so in general, the forward function, okay, does not commute with the complement operation, and does not commute with the intersection. It commutes only with the union. Okay. So this is the example. right? But we have the intersection contain the intersection of EI. Okay. So even though F and the intersection do not commute with each other, well, but we have the inclusion result. So this set is a subset of this intersection. Okay. But for complement, it's more complicated. Okay, more complicated. Any case, okay, there is no containing at all in some cases. So that complement more complicated. But for intersection, we have this. We have this inclusion. Okay, so inverse mapping is very nice because it commutes with our set operations, complements, union, and intersection, which is very important in the calculus of probabilities, because we usually consider the complement, the intersection union of events. Okay, so there are a lot of things. Okay. Any questions about the statements of proposition 4.1.8 and this remark? Right, if no, then we will give a proof of these three properties. All right, so here, right, so that X is in, so to show that they are the same, if and only if okay, by definition, okay, so if X is in the inverse mapping of complement of G, then the value of X should be in the complement of G. So that f X, okay, does not contain in G. So if f box is not contained in G, which means that X is contained in inverse mapping of complement outside of this one. Okay, so these two sets are the same. Okay. Any questions? Now here, which means that f of X is in the union, which means that f of X is in G sub I for some I. Okay, because union means for some. Okay, and which means that X is in the inverse mapping of G sub I for some I in I. Right, so function values in GI means that X is in the inverse mapping of GI by definition, because definition is very clear here. Right? So an element A is in the inverse mapping of G means that f of A is in G. So they are equivalent. All right, so which means that A is in, if and only if f of A is in G. This is the definition of inverse mapping. So you should know that. Right, so X is in the inverse mapping of GI for some I, which means that the union, X is in the union of the inverse mapping of GI. Okay. Third, X in the inverse mapping of the intersection if and only if f of X is in the intersection GI, which means that f of X is in GI for all I in I, for all. Intersection means for all. Okay. Now, so it means X is in the inverse mapping of GI for all I in I. Okay, so this means that X is in the intersection of GI. Okay, the end of the proof there. All right, so we are ready to state a precise definition of a random variable. Okay, a real value random variable. So in this course, we will deal with real value random variables. X on the sample space. X is a function from the sample space to the set of all real number R such that the inverse mapping of a Borel set B, right, is an event of interest in F for any Borel set B in the Borel signal algebra V on R. Okay, so for every Borel set in the real line, okay, the inverse mapping under the function X is an event of interest in F. Okay. Note that X induce a function from so in general here, right? Because as a general function, right, from the sum space to the set of real numbers, it induces an inverse mapping, right? This is from the power set of the real line to the power set of the sum space. The required general property okay, so the general property, oh, just required, okay. Asks for the restriction when we restrict to the Borel sigma algebra. Okay, the power set of the real line, of course, is a sigma algebra, but it's too big, right? Very, very big. But when we restrict only to the Borel sigma algebra, so Borel sigma algebra is much smaller than the power set bar. All right, so we restrict the domain. Then the codomain should be F. We ask for that. Okay. Because in general, if you restrict B, the only thing you can see is still the power set of X in general. Okay? So this is always true. This is always true. And then the restriction okay. All right. So even you restrict only to the Borel set, then the Borel set give after the inverse image of Borel set is in general just a subset of the sum space. Then the required general property asks for that. When we restrict to that, the codomain can be replaced by the F sigma algebra, which means that the inverse mapping of every Borel set, all right, is an event of interest. Okay, so this is the requirement. All right, this is the requirement. So any functions from sum space to the set of a real number satisfying these properties is called a random variable. Okay, I think I have to stop here, and I will continue the discussion on Thursday. Remember, the next Thursday, we will have the first midterm examination. And the coverage is from chapter 2 to chapter 4.